Hi everyone, my name is Shui Yan. I'm here to present combinatorial correlation clustering. This is a joint work with Vincent Cohen-Adad, David Rasmussen-Locke, Marcin Filipczuk, Mikko Torup, and Hanwen Zhang. So in this problem, we are given a complete graph G where each edge is labeled with either plus or minus. And we want to partition the vertices into several clusters and minimize the cost, which is defined as the number of internal minus edges plus the number of external plus edges. So intuitively speaking, we want them to be several disjoint cliques, and we measure the difference between them and the cliques. This problem is APX hard, and we know that it's impossible to have a 1.01 approximation polynomial time unless p equals to np. And the best approximation algorithm is a 1.437 approximation algorithm, which uses LP rounding. And these LP-based algorithms are not so efficient. So if we want more efficient algorithms, we will want combinatorial algorithms. And the best combinatorial algorithm is an old and simple pivot algorithm almost 2 decades ago, where in this algorithm, we randomly select one vertex as pivot, and then we create a new cluster consisting of this pivot and all of its neighbors, and we repeat in the remaining graph. So this simple algorithm is 3 approximation algorithms, and it can be run in linear time. And recently, people found that it can also be implemented in a massively parallel computation model. In constant runs, we can achieve a 3 plus epsilon approximation. And it can also be implemented in a streaming model where we only have O tilde n space. And in one single pass, we can achieve the same approximation ratio. Well, on the other hand, there is a sublinear time algorithm, which is also a constant approximation algorithm, but the constant is very big. Well, in the remaining part of this talk, I will show our local search solution, which has a below 2 approximation factor, and it can be implemented in all of these models. Okay, so let's consider a simplified case in the beginning. Assume we are able to enumerate clusters from a set S, where S contains all clusters in optimal clustering scheme. So which means we are able to have some candidates of the optimal clusters. And we just maintain a clustering scheme, LS. Whenever some cluster can improve our solution, we just insert it into our solution. Here by insert, I mean we grab these vertices from their original clusters and we create a new cluster for them. So we do this until no clusters in C can improve our solution, which means no cluster in optimal solution can improve our solution. Well, this is the only property we need for the future part. Now let's focus on one cluster C, the optimal solution. So we know that C cannot improve our solution, but what does it mean? So in this picture, I draw our solution as a black solution. The red solution is the optimal one. So if we focus on this C, we just look at all edges incident to C, so including the internal and external edges. So we can divide these edges into 8 types. So in this picture, we have 4 types. Type 0 edges are the edges which are internal in both solutions. and type 1 edges are which are internal in optimal solution, but external in our solution. Similar for 2 and 3, we can look at this picture. And then based on whether it is a plus edge or minus edge, we can then divide all of them into 8 types. And let's look at the improvement of C if we insert it. Then we'll find that type 0 and type 3 edges will not affect anything because, well, if they are together, the old solution, then after inserting C, they are also together. But for type 1 edges, in the old solution, they are external edges. But when we insert C, they becomes internal edges. So every type 1 plus edge will contribute 1 to the improvement. Every type 1 minus edge will contribute -1 to the improvement. Similarly, every type 2 minus will contribute 1, and every type 2 plus will contribute -1. Okay, so we know that the improvement must be non-positive, so we can have this inequality. And here, we only consider the edges incident to C. But then we can sum up the inequalities for all clusters in the optimal solution. Then we look at all edges. And notice that type 2 edge will be counted twice because they are incident to 2 different red clusters. But type 1 edges will only be counted once because they are internal edges in the optimal solution. So if we sum up the inequalities, we will get this inequality. So here x1 plus means the number of type 1 plus edges. Similarly for other terms. Okay, how can we use this inequality? Well, if we look at this picture, actually we can also write down the cost of our local search solution and the cost of the optimal solution. So the cost of our solution is just x0 minus plus x2 minus, so these are all the minus costs. And x1 plus x3 plus cost. Well, we can compare our cost to the optimal cost, then we find that the x1 and x2 are different. x0 and x3 are the same. But notice that we can use this inequality for the x1 plus and x2 minus in the cost LS. So we can get the cost of our solution is at most twice the cost of the optimal solution minus some terms. Well, this means our local search solution itself, it's a 2 approximation. Okay, now how can we go below 2? Well, now we assume that the approximation ratio of the local search solution is greater than 2 minus delta. Then we can see that the sum of these 4 terms must be smaller than delta times cost of optimal. And what does this mean? So it means that the minus cost of the local search solution and the minus cost of the optimal solution must both be small. Well, because the cost of the local search solution is just x0 minus x2 minus, and similarly for the opt. And also this x3 plus, this is the common plus cost of our solution and optimal solution. So here I just use this notation to mean the number of plus edges which are paid in both solutions. Okay, so we know that these 3 terms must all be small. Well, this means the local search solution must be very different from the optimal solution. Well, is this possible? Well, it is. So in this example, we can see that if our local search solution divides the vertices three vertical clusters, and the optimal solution divides them into two horizontal clusters, well, then all of these terms are zero, and the approximation is exactly 2. So this can happen. But we also notice that if we have three different clustering schemes, so if we have three clustering schemes satisfying similar conditions, the minus cost of each of them is small, and the common plus cost of each pair of them small. Well, that just means they are very different. And if these 6 terms are all small, well, it's impossible that all of them are zero. So we are not proving here, but we will go back to this claim later. But now let's first see how can we construct such smooth solutions. So we already have two solutions, which is our local search solution, optimal solution. And the basic idea is that we just run the local search twice to get another local search solution. Well, now we have two local search solutions, and we have these two properties for each local search solution. So we know that these 5 terms are all small. And if both of the local search solution are not so good, well, intuitively, this shouldn't work because the two local search solution can be just the same one. LS1 and LS2 can be the same solution. So the missing term, the common plus cost of LS1 and LS2, if we know that it is small, then we know that LS1 and LS2 must be different. But how can we make it small? Well, in the second round of the local search, we run a local search on a slightly different class. So we double the weight of the external plus edges of LS1. That is, the plus edges paid by LS1. So if we compare the cost of optimal solution, well, from the old graph to the new graph, the cost of optimal solution will only be increased by a small amount. Actually, it will be increased by this term, the common plus cost of LS1 and opt. And we know this is small. On the other hand, the cost of LS2 will be increased by the common plus cost of LS1 and LS2. So if this term is big, then what happens? Then when we go back to the original graph, we will know that LS2 is a very good approximation because it is a 2 approximation in the new graph. And when we go back to the original graph, the cost will be decreased by this amount. So we know that the common plus cost of LS1 and LS2 must also be small. So now we know that these 6 symmetric terms are all small. And in fact, the exact constant is that the sum of these 6 terms can be bounded by 4 delta times cost of optimal. So now we will show that we can use a pivot algorithm to construct a new clustering scheme with a cost at most twice of this amount, which is 8 delta times cost of optimal. Well, this means that the sum of these 6 terms cannot be too small because this 8 delta must be at least 1. Otherwise, we get a solution which is better than optimal solution. So this is a contradiction. Okay, so now let's see how we do the pivot. So we first associate each vertex with a three-dimensional coordinate vector. Well, the coordinate denotes which cluster it is in the three solutions. So if two vertices share the same x coordinate, then they are in the same cluster in, let's say, LS1. Similarly for the y and z. And then we define the distance of two vertices with a Hamming distance of the coordinate vectors. So if two vertices have a distance 2, then they are not in the same cluster in two of the three solutions. And based on the distance and plus minus, we can divide the edges into, again, 8 types. Well, we will use plus I to mean a plus edge of distance I. Okay. Then we will find that 5 of the 8 types are actually covered by 6 terms. Well, if we look at -0, -1, and -2, so these edges are paid in at least one of the solutions. So they are covered in the sum of the minus cost of the 3 solutions. And +2 or +3 edges, they are paid at least 2 solutions. So they are also covered some common plus cost. So these edges are covered in the 6 terms. So the cost of these edges can be bounded by 4 delta. Then we are going to charge our +1 cost to -2 and +2 edges, just edges of distance 2. Okay, so this is our algorithm. It is also simple. So we just select a coordinate vector with most vertices. And then we create a new cluster consisting of all vertices within distance 1. So we can look at this picture. We select this coordinate vector as the pivot center, and we just take the 3 axes. And we repeat this. Okay, now in each step, we can see that like these red edges are the possible +1 cost, and we can bound it, so we can charge them to the red edges. These red edges are distance 2 edges, and they will disappear after this step. So we can charge the red ones to the green ones. Okay. So we can charge our +1 cost to distance 2 edges, and we will never pay for +0 and -3 because distance 0 pairs are always together. Distance 3 pairs are never together. Okay, so the sum of the cost 8 types is at most 4 delta plus 4 delta. So that is 8 delta times the cost of optimal. Then we know that one of the local search solution is 2 minus 1/8 approximation, because delta must be greater than 1/8. Okay. So we can further improve the approximation to 2 minus 2/13 by more rounds of local search. So we just did 2 rounds. So if we can do more rounds, then we can make the approximation ratio close to 2 minus 2/13. But I don't have time to explain the details here. Okay. Then let's look at the implementation of local search, because we just assume that we can enumerate the clusters opt, but of course we cannot. So instead, we are trying to guess the optimal clusters by some sampling techniques. So here I will roughly explain what we did. So we first run the pre-clustering algorithm, which is the constant of approximation algorithm in a sublinear model, and it can also be implemented in an MPC or streaming model. So the greater than 500 ones. And the pre-clustering will pre-cluster some vertices, atoms. These are vertices that are always together optimal solution. And it defines the admissibility of every edge. So if an edge is admissible, then they are allowed to be together. And then in each round, we select each vertex as a pivot with a probability inversely proportional to its degree. So in one round, we can have many pivots. And we know that for each pivot with constant probability, the admissible neighborhood, which are the vertices that are allowed to be together with that pivot, is almost disjoined with others with constant probability. And for this pivot, we will try to generate the cluster containing it in the optimal solution in a parallel way. So we proved that in each round, for each pivot with constant probability, we can get a cluster close to the correct one, which has a similar improvement. And then in one round with constant probability, we can have a constant fraction of the total possible improvement. And then we can boost the probability by running theta log n copies in parallel. Then we have a high probability result. Okay, so finally, it can be implemented in the MPC model, sublinear model, and streaming models by a lot of sampling techniques. Okay, that's it. Thank you for listening.